Hello, my name is Jana Sajdakova and I am a PhD student at Bath University. This PhD research is aligned with the Trend Research Group. The presented paper is entitled Mapping the Competencies of Design Engineers Against the Jantsch's Hierarchical System. The aim of this paper was to identify and compile current competencies related to design engineers from literature and use this profile to classify competencies in disciplinary terms. The main focus was on identifying if any of the current competencies have TD attributes. The current research has identified that to meet the future societal needs such as climate change and grand challenges of engineering, it will be necessary to adopt transdisciplinary methods of working. TD offers higher level of analysis compared to other disciplines, with TD approaches being adopted for problems which are large, complex, unpredictable and ill-defined, and that require contribution from a range of stakeholders working to a common goal. TD has been adopted in other fields. For instance, in sustainability and medicine, where the need for collaborative working, bringing together experts from different disciplines in order to solve complex environmental and public health problems, is essential. TD in engineering. The future societal problems as well as challenges linked to fast technical developments like the implementation of Industry 4.0 or building a smart factory can be defined as large, complex engineering problems that will require a TD approach. This change in context of engineering leads to a rise in demand for new engineering skills to reflect more complex and cognitive future jobs. However, there is little in the engineering design literature that identifies how to assess the transdisciplinarity of people, tools, or project teams, and how to determine whether the engineer is able to work in transdisciplinary manner. Testing if Jantsch's framework can be used to identify disciplinary competencies. Research approach. Relevant literature was identified by following the steps of the systematic literature review process. A search string contained term design engineer and at least one of the following terms: competence, ability, skill, capability, behavior, knowledge, and attitude in title, abstract, and keywords. Scopus database was used to conduct the search. From a total of 2,398 results, 7 papers focusing on practicing design engineers were relevant to this analysis. Using thematic analysis, competencies were extracted from the text and compiled into a profile of 117 competencies. These were individually mapped based on their disciplinarity against the Jantsch's TD hierarchical system. Competency mapping. Jantsch's pyramid is a multi-level, multi-goal 4-level system. It consists of empirical, pragmatic, and normative level, and at the top of the pyramid, purposive level with societal values and meanings. Different types of coordination and cooperation take place across the levels, involving the interaction of a range of actors, and these define different disciplinarities. Jantsch defines 5 disciplinarities, and our model for classifying disciplinary competencies was designed by formulating 2 questions based on definition of each discipline to describe the nature of these interactions. Multidisciplinarity takes place on one level, involving a variety of disciplines, but there is no cooperation. It relates to a designer working within the engineering disciplines in isolation from other applied disciplines. Interdisciplinarity takes place across 2 levels, with discipline at a higher level organizing related disciplines at a lower level. Jantsch further divides ID to describe the level among which they interact. First one is teleological ID. Engineering design as an applied science sits within the pragmatic level and interacts with sciences at the empirical level. Related competencies are linked to the capitalization of scientific knowledge from an empirical level and applying this to engineering tasks. Normative level or normative ID refers to engineering interacting with other applied sciences in a pragmatic level while adhering to norms, rules and policies set at a higher level. It includes design engineers whose role is the development of innovative technological alternatives. Relevant competencies cross the normative level boundary and allow design engineers to cooperate with a wide range of stakeholders and recognize different points of view and requirements. The last ID is purposive ID. It only crosses normative and purposive level, which is above engineering, and it does not integrate scientific disciplines, thus it's not applicable to engineering. The one we are interested in is transdisciplinarity. The transdisciplinarity can be achieved by integrating all other levels. It's about the interactions up and down and across all levels of the pyramid, between disciplines, across project boundaries, between academia and industry, while the purpose is incorporated across all levels of the pyramid. Competencies relevant to TD will enable the integration of requirements and values of different stakeholders by recognizing the purpose. Related questions are, does the competence demonstrate purpose consideration, or does the competence demonstrate value recognition? There was a number of competencies that were lacking context and we were unable to assign their disciplinarity. The developed questions shown in the table were used to identify disciplinarity of competencies from the sample studies. Disciplinary competency classification. We were able to classify over half of all competencies. 3 multidisciplinary competencies were related to awareness or experience of other departments within organization, but without cooperation or integration of the knowledge. The largest group is teleological ID. This is not surprising as this group represents competencies related to technical aspects of the design engineer's role. We were able to map all technical and design process skills to this level. Other competencies related to the design task include cognitive abilities such as critical thinking, abstract thinking, and analytical abilities to evaluate an idea. One competence was describing a tendency to work alone, focusing creativity purely on technical aspects. Such a preference can be a good indication if the person is suitable to work in TD manner. The second largest group is normative ID. Competencies that were included focus on awareness of different stakeholders, knowledge of wider business environments, and knowledge and compliance with codes and standards. 5 transdisciplinary competencies were identified. First 2 related to engineers' ability to think from a stakeholder's perspective, how and for what purpose they use the product or service, and what value they were getting from the use. The third competence implies awareness of stakeholders' requirements, but only by implementing these requirements the purpose is recognized. Competence 4 and 5 implies understanding of complexity, purpose and value of the project. Remaining 50 competencies were general competencies without any disciplinarity. Although mapping decisions are subjective, what is clear from this analysis is that the context is important for disciplinary classification. For instance, general competence, intercultural communication, with context translates to disciplinary competencies at all levels. From this analysis, it can be concluded that although the role of design engineers is crucial to the product development process and to meet future societal needs, there is a gap in engineering design literature with no TD designer competency profiles. It is possible to classify competencies based on their disciplinarity, and TD competencies can be identified using Jantsch's definition of TD. Also, context matters to disciplinary classification. Finally, future work should focus on determining the way to measure current competency levels against TD competency requirements for TE projects in order to identify gaps in training and curricular requirements. Thank you.